thing, yeah, since most of us are here today, so I would like to resume our weekly meeting since next week. So so here today. So I would like to yeah, so I probably will send an email to ask everyone to share with me your preferred time, but I prefer we're gonna finish our weekly meetings in the Monday and Tuesday, and so that we have like several like Wednesday through Friday to do our own things, and also I'm considering to make our group seminars to be more regular, not like random like last semester. Okay, so Da, I think yeah, you can present now.
Okay, so actually I just started to look into the large language model like 2 weeks ago. So I'm not an expert. So maybe when I go through the seminars, you can like correct my mistakes or anything. Yeah. So yeah, well, so I start from the very beginning. So everything is begins with the first paper, the attention. So
Yeah,
yeah.
you want to click the slideshow button on the top right.
Oh, I'm going to so most of the time I think I will go to the paper and then
Oh,
yeah.
okay. Okay. Oh, that's
So
good. Okay.
yeah.
Okay.
So everything goes from this paper. So in this paper, Google proposed the attention structure, but their goal is not for training a pre-trained language model. So their goal is just to do a translation task. So it's basically a sequence to sequence prediction. So as you can see, this is the model structure. So the input is the original language you want to translate, and the output will be the target language. So it's basically a sequence to sequence model, but this model replaced the RN structure. So it has like several benefits. At first, you can, so when you train the RN, you have to train sequentially. So actually, it's very costly. And if you do the transformer, and then you can train the model like in like with all of the I mean in your batch, like you don't need to get the prediction like sequentially. You can like do the prediction in parallel. So compared to iron actually is a must to at training. Also like so attention structure is more robust. And the iron has a lot of issues like forgetting or something. So transformer don't have that kind of issue. So Google proposed this structure, but their goal is just to do the translation task. And also, if you look at the structure, so in the very original transformer, the normalization is after the module like attention, after the attention module, and after the MLP module. So it's called usually this is called the post normalization, and I think they use the layer normalization. And also here, so this is the input. So when the input interacts with the output, it happens during the cross attention. This is the cross attention. And except this one, all of the attention are self attention. So this is
Wait a second. So I think one advantage of attention over the RN is RN you need to compute to the state by state, right? Across
yeah,
the but the attention can do this in parallel.
yeah, in parallel. So yeah, like for example, like if you want to uh like take any sentence as example like here. So in RN, in each iteration, you can only get the one token at a time. But in transformer, you can in parallel get all of the token. all of the prediction for all of the tokens. But in R you have to do the in parallel or in sequential. So that's the benefits of the transformer in terms
That's
of the
mainly for training, right? But
yeah
for inference, you still have to do it one by one.
yeah that's for training, because in inference you don't know what the future will look like, right? In training, but you do. So in inference, you still have to do the like step by step.
Okay, another thing I think it's better for you to explain what does it mean for layer norm. So I assume those yellow block like add and norm. Add is it actually is skip connection, right? And
Mhm.
norm, how do they implement layer norm?
So the neo norm it just like normalize the features, uh
Normalize features.
like something like so I think the neo norm is on the feature dimension. Like if you have D features and then you want to initialize like D lambda and D beta, and then so
Assuming each layer can be viewed as a feature vector and do a normalization.
each layer,
Yeah.
yeah. In each layer, so it has n layers, right? So in each layer, it has like normalization.
Okay.
So like I think they always do the layer normalization whenever there is a module. Like this is the MLP module, this is the cross attention module, and this is self attention module. It's pretty standard in the current transformer architecture. But the
Right
difference
now,
that
yeah,
mhm.
right now is a layer norm applied before the attention block or
Yeah,
after?
we will like go to other models like the Llama and the GPT. So they mostly they use the pre-normalization. It means like they put a normalization before every module, right? So in the original transformer, they put the after the normalization.
And do they apply how do they generate the QKV matrices? Do they use MLP or just use one linear layer?
I think all of the attention they just use a linear to generate the QKV.
I mean from the embedding, right? From the embedding for each token, they just use a linear layer to generate the QKV, three vectors.
Yeah, they just use a linear. Yeah, I'm sure. Yeah.
Okay. Okay.
Yeah, there is not much modification in terms of the attention itself. Actually like there is not much like model architecture difference for all of the large language models.
Okay, the only difference is how do you choose the number of heads? How many
Yeah,
self-attention layers and the cross-attention layers?
yeah. The difference maybe is in the like what the normalization you use, or how do you choose the position encoding. That's the key.
Position encoding isn't position encode just the sine cosine to some power?
So I think in this paper they use the absolute position encoding. They usually call this one. So it basically means they treat each position as independent uh, IDs, you know. So they assign variable to each ID, and then they call this as absolute position encoding. So in the later, if we see other models, they maybe use like relative position encoding. So for example, if the position 1 and position 3, they have like it's a distance 2, and then this position encoding is similar to any other two tokens if the distance is 2. So they maybe use like relative position encoding. And also in the
It's
latest,
relative to the first token in the sequence you want to predict, or
um, actually I don't know about the detail, but the general idea is like this.
I mean, it's just the standard attention. Oh, this
Yeah,
is position encoding, how they compute position encoding.
yeah. I mean, this is the relative position encoding they use, but the I think the newest paper they also like abandoned this position encoding, this relative position encoding. nowadays maybe they use the what is it called, the meta. Yeah, it's a position encoding from meta paper. We will go to that.
Okay. Okay.
Okay, so yeah, this is the attention. So they use 6 layers of so they call this block as encoder because yeah, so this block, the right part is called decoder. The difference is that in the decoder, because they have to, you know, when you do the translation, actually you cannot foresee the future prediction. So they apply the mask structure to the output. So that's why they call this like casual attention, casual transformer is called the decoder. And this for the encoder, because when you do the translation, actually the original language you can actually at the beginning you can see the whole sentence. So they don't need to apply a mask over the input. So they call this as the encoder. And nowadays all of the large language model they just use a decoder.
So, okay, so how do they apply the mask during training? You should
Uh,
explain.
your training, so for example, if you output, like have like 10 tokens, right? So you have to predict the 10 tokens one by one. And when you for example, if you want to predict the fifth token, you can only utilize the first 4 tokens to predict the next one. So actually, to predict the fifth one, you cannot use the 6, 7, 8, 9, 10. So that's why they put a mask over the 6, 7, 9, 10 tokens. It basically just when they, if you have 10 tokens of output, you have like, when you do the attention, you have a 10 by 10, the weight matrix, right? And then when you want to calculate the embedding for the fifth token, you have to mask out the value of the 5, 6, 7, 9, 10. You can only keep the first four first 4 weight matrix of first 4 weights, and then it basically, because after you get the weight matrix, you do a softmax, right? So basically, you just need to replace the invalid positions with the minus infinity, and then it just basically means it want to involve in the calculation of the embedding. So that's how they do it.
Oh, okay, so they mask out the fifth to tenth tokens and just calculate self attention from the first to the fourth token.
Yeah. And they do it by replace the values for the 5 to 10 tokens with minus infinity. That means, so when you do the softmax, it doesn't contribute to anything.
Okay, okay. And they only predict, actually they predict a softmax vector to as the representation of the next token, right?
Yeah,
Okay.
they just use the first 4 tokens to get the representation or the embedding for the prediction of the fifth token.
Okay. Yeah. Yeah, that sounds reasonable. So yeah, continue, please.
Yeah, so that's the difference between the encoder and decoder. The decoder apply a casual mask. They call it like as a casual mask, and the encoder they did nothing. They just use they don't apply a mask. And in this paper, they they didn't discover the potential of the transformer. So they just apply it to a translation task. It's a sequence to sequence prediction. And yeah, and they use a 512 dimension and 8 heads, 6 encoder layers and 6 decoder layers. And then after the paper, so this is the first version of the GPT-1. in this paper, let me check. So in the paper, they claim they use a very original transformer decoder. So it means they use the same structure as the attention paper. So
Can you enlarge a little bit more?
yeah, but they enlarge it a little bit more, and they say they use like 12 layers, and they also use you can say they use the post layer normalization. It means after the attention and the feed forward. And I think they also use the same test and position embedding, but the difference is that they use a larger model. And let's see, where is the okay, let me here is a model, 12-layer decoder only transformer. So they enlarge the dimension, and they also use like 12 heads.
So the 768 dimensional states and 12 attention heads. So they mean they actually even each attention actually is working on this 768 over 12, right?
Yeah, in total there is 768 dimensions.
Okay.
And I also noticed that like in the models, they, for example, in this paper, for the MLP, actually they use a larger dimension for the MLP only. So they use 3,000 and more dimensions. So it's much larger than the attention.
How many feed forward layers did they use after the attention layers?
Just one.
Oh, so okay, they do this once they do this after every attention block.
Yeah. So they call this as a layer, and each layer has a self-attention and a feed forward.
Oh, I see.
So so there is no changes to the attention paper, but they just like use a larger model.
And okay, another thing. So for text and the position embedding, so assume that they get the token embedding from some like pre-trained, say word-to-vec model, and then add the position encoding, right?
So in terms of the testing in tokens, I think some of them maybe they just randomly initialize the tokens and they learn the tokens. So maybe they don't need to load the pre-trained tokens for other models. Yeah.
Oh, really?
I
Yeah.
think they use the BP encoding.
BP coding.
Yeah, you just I think in that paper they say it's a BPE. I think it's byte pair encoding. Yeah.
By
Oh,
parent.
yeah. In this paper, that they
So
maybe
I think it's different from the word byte. So it's not like a word is embedded. It's more it's like a byte.
this is
Yeah.
definitely not a word level embedding.
Okay.
Yeah.
So that means they maybe for example, if one English word, it has like maybe it can be decomposed into several like subwords, and then they will add them to the vocabulary. So that's why. So I remember if you for the GPT-2 actually have like 50,000 vocabulary size. So it's
Okay.
huge.
Okay.
So so they say the GPT-1, and for the GPT-1 actually is also not a pre-trained model. So it's not the large language model we usually use. It's still actually is indeed training on a larger of text, but actually when it doesn't discover at that time, OpenAI hasn't get the conclusion that a pre-trained model can do many substring tasks without retraining, without pre-training. So in this paper, they actually just train the model, and then for the substring tasks, they also need to fine tune extra parameters. For example, like for the classification, they need to train another linear layer to do the classification. And for the other tasks, like compare to get a similarity of two blocks of tests, they also have to train another linear layer. And also for the multiple choice question, they also to to train other 3 linear layers. So in this model, it's still not a large language model as we imagine.
But were they trained on very large
Yeah,
data set?
yeah, they pre-train on 7,000 unpublished books.
Okay.
But yeah, this is the very first paper to train the model on with the unsupervised learning. It means like they just predict
This should be the first decoder only.
the first decoder only to train an unsupervised learning task.
Okay.
And actually also the first paper to train an unsupervised learning task. Because in the attention is a sequence prediction, you have to create a label, right? But in the GPT-1, you don't need to create a label. You just put all of the tests into the model and do the unsupervised learning.
Okay.
So you can say is also the first paper to do unsupervised learning. Yeah, and so but for the substring task, they have to fine tune and train extra parameters. And then there is a GPT-2.
So those papers are also published by OpenAI?
Yeah, so the GPT series are all published by OpenAI.
Okay.
So in the GPT-2, I think, yeah, in the GPT-2, they is a 1.5 billion parameters model. So there are a few changes. So in this paper, they put the layer NOR before each attention and MP block, and then another change is they add addition layer NOR after the final attention. So if you compare the let's say, what does it mean by final attention? So in the decoder, actually, I don't know what does it mean. In the paper, they say they add an additional layer NOR after final attention. But
So after final attention, they do a additional layer norm, and then they do a linear and then MLP, right?
yeah, I thought the last layer actually is made of attention and the feed forward. What does it mean by the last attention? Oh, I say what's the point? Because you know they put the layer node before the attention and the MLP.
Yeah.
Oh, so then in the final attention they put an additional layer node after the final attention.
Yeah.
So yeah, that makes sense. Okay. Yeah, this is the like model changes, and then they also use a larger vocabulary size, so it's more than 50,000, and the training data is 40 gigabytes. Yeah, and then they also increased the context size, the training context size from 500 and to the 1024, and they use a batch size of 112. So yeah, they use a lot.
So what does it mean for context size? Is like the total number of tokens in a sequence?
Yeah, in the training, you have to define a maximize training sequence. So it means the maximum sequence length is 1024.
Okay.
I think this somehow relates to the position encoding, because in the GPT-1 and 2 they use the absolute position encoding, so they have to predefine the position encoding, so they have to define the maximum sequence length.
Okay.
In the later the language model, they use in the Llama they use the rotary embedding for the embedding. So I think in this embedding you can use as long as how many sequence length you want, you can use any length. But in the GPT-1, GPT-2, you have to predefine the maximum length.
Okay.
Okay, but this paper is
large.
you use a larger model, and then you also pre-train a large amount of test. But
No, that enlarge that text. It's not very clear.
okay, so actually I'm not go to the details of the test, but I will I'm checking it. So
No, I mean you can you make the PDF larger, the text larger? Yeah. No, the paper. Yeah.
okay.
Okay. Yeah.
Where's the data? Oh, here. Yeah, they created a new web scrap. So they emphasize the document equality. Yeah, they have to filter that by humans. Oh, from Reddit. So
What does it mean? Do they add some human labels?
I think it's just if they have 3 comma on the Reddit, it means a good response.
yeah. So this one it actually means the web page they use, it has to be filtered by humans. And for example, for Reddit, if the post or it had at least 3 comma, maybe it's 3 thumbs up, and then they think is a good quality source, and then they put it into the data set.
Okay.
And then so the resulting data set, the web test, so is 40 gigabytes.
Okay.
And also they remove all of the Wikipedia documents.
Oh, really? Why?
I don't know, but I know Meta, the Llama, they use Wikipedia documents.
Okay.
They said maybe overlapping training data with evaluation tasks. So maybe they don't want say the leakage, so they just remove the Wikipedia documents.
I think there was actually a cool anecdote. So I think GPT-1 was published by OpenAI, and then it was beat by the Google BERT. So on the GPT-2, they do minimal changes on the model. They just put a lot more data, and GPT-2 just suddenly got really good performance and surpassed the BERT.
I don't know much about BERT, but I think in early years, the GPT-1 or 2 compete with the Google, but the BERT, the Google think maybe the BERT is not a decoder only, so maybe it's still the encoder decoder only,
Yes.
or encoder and decoder structure. But later, OpenAI proves that decoder is more powerful.
Yeah, interesting.
Okay, so yeah, and this GPT-2 actually so is pre-training a larger amount of tests, and then OpenAI starts to discover that they don't need to do the fine-tuning with extra parameters like GPT-1. In the GPT-2, they can directly do the zero-shot experiments in the you just need to give the prompt to the model, and then the model will try to do the completion. And when the model do the completion, they will answer your questions. So they discover the ability or the power in the GPT-2. Yeah, they prove the language model can perform tasks in zero-shot setting. Yes, okay. So this is the GPT-2 paper. And then so GPT-3. So 3 just reuse the GPT-2 model. So there's no changes to the model itself. But they like massively increase the parameters. So it's like 175 billion parameters. I think this is not true. So okay, so they also increased the content sets from 124 to 2048. So in this paper, the structure is the same, but they just increase the model size.
Are they trained on the same data, or they also enlarge the data set?
Let's say I think they should enlarge that. Yeah, train data set.
Yeah, it looks like they have more data set than GPT-2, right?
Yeah, they should have like more data sets. But I think their goal, like their idea is that they need to use high quality data sets. So this is different from the Meta Llama. Llama use like no matter it's good or bad, they don't filter, but they just use all of the tests.
Yeah.
Yeah, and in this field, they define the zero few shot in learning. So few shot learning means when you give the model prompt, you give some examples. And then when the model trying to do the completion, they can follow the pattern, like follow the example you gave, and they will answer the question. And the one-shot learning means just give the prompt one example. Zero-shot, it means you don't give example, you just directly ask the question. And then the model trying to complete.
One question. So for the few shot and the one shot, do they still change the parameters?
Oh, they don't do they don't change the parameter. So that's one of the places I'm confused. Like they call it like learning, right? So
It should be called
I
prompt, right? A few shot learning should be called a few shot prompting.
yeah,
Zero shot should be zero prompt.
yeah, but they call it learning, so it's confused. Maybe they meaning the model will try to learn the pattern in terms of the test data or the prompt.
so I'm not sure if what I'm thinking is correct. So it's like we give them some example and with the answer. Let's say we give them a question and answer. So and with like few shot or one shot or zero shot, with few shot or one shot, like so like decoder takes that as input and they try to find the pattern from our input.
Yeah. So they usually
Oh.
call a prompt as a context. So you give the context if for the in the one-shot learning, in the prompt, for example, you want to do the translation task, and you will give the model example like you want to translate English Chinese, and you give the English, and you also give the Chinese, and then this is called one example, and then and then you raise another question like help me translate this sentence. In this time, you just give the English, and then the model will try to complete and give you the answer. But in this case, you actually give one example, and that's why it's called one-shot learning.
I see. So the attention mechanism is working on the example we gave.
Can you ask that again?
So let's say like so I'm not sure about like really clear about the mechanism for one shot and few shot. So is that like we put that as input, like some like question and answer as input, and then like we gave them like actual question, and the attention was like trying to look at the example we gave, and then attend our question, and then give us the output.
Yeah. So actually, what do you input to the model is the prompt, right?
Yeah.
And when you give the model prompt, they will try to predict the next token. So just like the attention mechanism, when they are trying to predict the next token, they will take all of your prompt or all of the prompt tokens, and then calculate the attention scores or something, and give you the embedding for the next token, and then and then they will go to the softmax and get the word.
Got
it. And you do this in the autogressive way.
Right.
Until the model reach a token, maybe it's a like end token. That specific token tells you that the answer is finalized. So you don't output any other new token.
Got it.
Okay. Yeah. So from the GPT, also in this paper, it also introduced the fine tuning actually. Okay, so in this paper, they try to like fine tune the pre-trained model. After the pre-training stage, what your model does, it just like it's just you can say as a token generator. When you give it some input, it actually just like predict the next token in some probability. But actually, the model, the pre-trained model still it doesn't have the ability to really answer the question. Like, I mean, the model doesn't have it's not what the people want. It's not the answer, or the answer they give is not, maybe it's not human readable, So they have to do another fine-tuning stage. In the fine-tuning, they basically it depends on task. If you want to get a chatbot, or if you want as a like question answering machine, and then you just give some data. The data is like question, answer, and then you put the data set into the model and then do the fine-tuning. So, and the training process actually is just like the pre-training, but your data set is a specific task, like question answer task.
Okay. I think here this page explains well the few shot, one shot. The few shot, one shot is just like I give you during the prompt. They give the examples. They give the examples. It's like, okay, here are a few examples about question and answers. They have like tags for question and answers. They give like 10 such tags, and then you keep typing like, please answer the following question, and then the model will generate the answers for you.
Yes, but the one thing I'm not like I think like when I learned the large language model before, like I don't understand is like if we don't change the parameters like in the few shot learning.
No, it's not. It actually is not few shot learning. It's just a few shot prompt.
Yeah, prompt.
There's no learning.
I see.
Yeah, once the model is trained, the model is there. It's fixed. What you need is just to provide different types of prompts. One type of prompts is like, okay, I give you a list of question and answer pairs, and as their condition or their context, now I'll give you, and then next I give you a new question and ask the model to complete the answer.
I see.
Yeah, and this ability actually, the model has a pre-trained model can do this, you know. But they fine tune the pre-trained model to align align with the humans like preference.
Yeah.
So the fine tuned data sets, for example, the data set is like question answer, this kind of data, and then they just feed into the model and just like exact the same training step, just like predict the token, and they call it like supervised fine tuning. Okay, so this is the GPT-3 paper. Okay, so after GPT-3, so Meta proposed their large language model, and actually it's like 10 times smaller than GPT-3. So, yeah, 10 times smaller. And then they do some, it's still based on the attention paper, but they have some model changes. So they also use the pre-normalization, but they use the RMS norm.
What is RMS norm?
I don't know. So they is a method introduced right here.
Okay.
You can if you want to use it, maybe it's a PyTorch built-in normalization.
And use a different activation function.
Yeah, they use the Swift loop activation.
Okay.
And the rotary position code embedding is a method they propose. Oh, it's not. Yeah, it's introduced by another group.
Okay, so basically they keep the same architecture. The only difference is how do they tweak the activation embeddings and normalization.
Yeah. So this is the only changes.
Okay.
And they also like use so the data sets, the idea is different from the OpenAI. So OpenAI use like they want to make sure the data is high quality. But Meta, so they claim the data they use is not about like personal sensitive like data. They all use from open source, and they don't care about the quality, and they just train the model.
Huh?
Also, they also do the fine tuning. So after fine tuning, they got the observation, the performance is improved, and the model is like is more prompt to follow the instructions.
But how do they where do they get the instruction following data set?
I think when the paper published at 2023, so at this time, I think the research community already like did a lot of the data sets work. So they just utilize the data sets.
Okay.
Yeah. And okay, so next I'll introduce the the fine tuning. So in the Llama 1 and the GPT-3, they just do the supervised fine tuning. It means they just do it as a supervision task, just like give a question and answer pairs, and then they do the supervision on those pairs. And nowadays, like usually people want to improve the quality of the answers of how the large language model answer questions. Nowadays they will also use the reinforcement learning to fine tune the model. So I will introduce the
one thing down before you talk about reinforcement learning. So for the instruction following fine tuning, do they only provide like instruction following pairs, and then they just fine tune with that sequence of
Yeah. So the data is like a question, and they definitely have like question start and end. The sign tokens. The token tell you that question starts and question ends. That's special tokens. So it's like question, and the question itself, and then the answer tag, answer, and then they put them together like in one as one example, and then feed it to the model.
Oh, so it's still like trained like a sequence, a
Yeah,
decoder.
yeah, decoder, still like next token prediction.
Okay.
But the data set is not like, but the data set is like very specific, like follow some tasks. Maybe it's a math problem, or the question answer pairs, or some domain specific the question answers.
Okay.
Okay. And then yeah, I will introduce the. So PPO is the most frequently used reinforcement learning technique. This one is also used in DeepSeek. So yeah, I will go over this one. So in reinforcement learning, the goal is to maximize the long-term rewards. So in this equation, the tau. So the p theta is a parameterize the policy. For example, in the large language model, it actually like predict the token. In the when predict token, it actually predicts a probability of the tokens. So actually, it sample the token or sample the trajectory from the policy. So the tau is a one trajectory. Or in the language model, you can treat it as the answer, like a series of tokens. And then for each trajectory, you will get a reward. And then do the summarization over the trajectories, and you want to maximize this objective. So to maximize it, you need to get the gradient. If we use the gradient descent to optimize the parameters, and then you take the gradient, and this one is a constant, and then you just need to take gradient over the policy, and then you can write down this one.
Yeah, this is the policy gradient, right? Why is it called PPO?
Oh yeah. I'm introducing the PPO like starting from the policy gradient.
Okay.
Okay, so yeah, and eventually you can written if you use this formula, you can write this as this one, and then it becomes this one. Is so the gradient over the parameter is equal to the reward multiplied by the gradient of the log of the policy. And the big N is like you sample N times, you sample N trajectories from the policy. So, and then here, so you can, because we predict the sequence in an autoregressive way, so you can decompose the probability of the trajectory into this one. Is a series of multiplications. Is from t equal to 1 to big T, and for each trajectory, each small n, and then the log of the multiplication is the summation of log. So you put the summation here, and also you can put the summation here. And then okay, and then you get the formula for the policy gradient. So this is the objective you want to get to maximize the long-term rewards. Okay, so this is the objective, but this one has some problems. The first, for example, if you so this equation will become this equation. So the reward will depend on the time, the steps the model is in. So it means that for example, like when you play again, if you are in the middle of the game, actually the reward for this time it shouldn't depend on the past steps. So that's why they use a reward for user at a time step for the reward.
So I mean the reward is not for the entire trajectory.
Yeah, it's not for
a reward for every step.
Yeah, for every step. Like
Okay.
we want to know the reward for the every step. Oh, it's not for this step, it's for all of the rewards starting from the step.
All of the parts starting from step T.
Yeah, starting from the step T, the long-term rewards starting from the step T.
I think this is called the reward to go.
Mm-hmm.
So basically, it's trying to reduce the variance. So
But you need to first give a definition, right? It depends on some kind of reward is defined on the whole trajectory. Some reward defined on is kind of like, okay, starting from this time point and until the very end was the accumulated reward, right?
I think this is a historical problem. So all the environment, they give the reward with each action. So given a state and the action, they give you a reward. So you always have the reward on the action step. And like they choose to use the reward to go is only to reduce the variance. So basically, like I think the whole problem with the reinforcement learning is like there's a trade-off between bias and the variance. So if we use the whole trajectory reward, it is unbiased. But if we use the reward to go, it is biased but low variance. But they found like in practice like low variance version always works better.
Okay. So that
Yeah.
can you explain what does B mean? B as NT, what does it mean?
Okay, so for example, I want to give you a like concrete like example. Like when you play a game, like for example, you are playing the super you when you play some game and maybe at time T you want to make a move, right? You want to select a move you want to choose. What if the game actually you are in a very bad situation? And in that situation, whatever move you choose, actually you will lead to a negative reward. Like you will whatever you choose, you will get better results. But in a game where you are a good position, and then whatever move you choose, actually you will get a positive reward. But that's very unreasonable, because in the game where you are in a bad position, maybe there is a move you choose will help the game. So that's why they introduced the B here. The B here is like the base rewards, like the average rewards over the current state. So you want to calculate the advantage over the base rewards.
But how do they get to the base reward?
I will introduce like later.
Okay.
So but the base rewards is over all of the possible actions. So you can see the input to the base is just the state here, the current state.
Okay.
So it's the average over all of the possible moves. And if your action is larger than the base rewards, it means your action is good, right? Because it's a positive value. But if your action, the rewards is not good as the base or the average, and then it means you're chosen or your policy is not good.
But this base reward will vary at a different step T, right?
Yeah,
I think the base,
base.
I think the base only depends on state.
Yeah, depends on, because it
Only
consider
depends on state.
yeah, because it consider all of the possible actions. So it just depends on the state.
Yeah.
And I want to add something like the reason why we include the baseline is because we still want to reduce the variance furthermore. It's like let me try to see how to explain. So the reward function is always positive, right? And like if we want to maximize it, it's always positive, and we just push it upward. But if we kind of like if we add in the baseline, we are kind of normalizing it to like a zero mean. We just want to, so there are negative parts, which can reduce the variance further.
Yeah, I think it's more like a active centric, right? There's some strategies is like subtracting some mean.
Yeah, exactly. Yeah. If everything was all positive, then the training will be like the huge variance. Because everything with time is positive.
Okay.
Yeah, I can explain like here, like for example, this is you and you're playing the game like Super Mario, and this is a monster. Like for current step, if you choose move right, and then you encounter this monster, and then you get maybe the immediate reward is like negative, but actually this R is the is the long-term rewards is positive, and then you still if you don't use the baseline, and then actually still encourage the model to move right. But the truth is that this actually is a bad choice. So you have to use the long-term rewards to minus the baseline, and then this one will be negative.
Okay.
Yeah, because in this game, actually, like in this step, your long-term rewards here is a positive value, but actually this action is not good, But you have to compare it with the other possible actions, like you can go up, you can go left, right? Like by go right, this action actually is worse than the other directions. So you have to minus the average of those actions.
I see. But why is that the long term the reward by moving to the right is still positive?
Because in the future, maybe you will get the coins, right? The coins maybe is 100, like the rewards.
Okay, but it assumes that the Mario when it meets the mushroom, it will not die.
Yeah, you have to assume that. I'm just giving you an example. Like you have to calculate the advantage of the current move over other moves to get rewards. So that's why you have to like minus the baseline here.
Okay.
And this maybe is aligns with the Zhitong said, like it reduces the variance.
Yeah. I think other literature talk about mainly express it in terms of like how to reduce the variance.
Yeah.
Okay.
But yeah. Okay. Sorry, so I prepared the presentation. I thought this was a personal presentation, so I use Chinese here.
Yeah, and no worries, you just need to explain
Okay.
In English.
Okay, so next we define some function, like we define the Q, the input to the Q. The Q is the action value function. So the input is the state and the action. So it measures the under the state, and if you do the action A, what is the expected long-term rewards? So this is the definition for the Q. And the big V here is the state value function. So it just means under the state, the expected long-term rewards over all of the possible actions. So it basically means like the way is the expected over the actions on the queue here.
Okay.
And then based on this one, we can define the advantage function. The advantage function over the state and action is the Q minus V. It means if I choose this action, A, what is the advantage over the average values? So the average is the V theta S here. So this is how we define the advantage. Okay, so we can plug the advantage into the equation previous here, and right. So there's the advantage over the action we choose, but the action. Oh yeah. So next we can decompose the Q as the function of V. So the Q over the current state and action is equal to, like, if we choose the action, how many the immediate reward, the small r is the immediate reward we get on the step T. And we add this one here is a discount factor. So it's discount factor multiplied by the expected long-term rewards of the time step T plus 1. So in this one, we get the QSA here.
But how do you know ST plus 1?
So
given ST and A, you immediately know what will be the state ST plus 1?
Yeah, even a larger longer model, like the A is the token the model predicts, right? And then the state, if we get token and we have the state T plus 1 is the previous the prompt plus the token we get. So we immediately know the state T plus 1.
Okay.
Okay. And then we can write down the advantage as this is Q theta minus the V theta. So we just plug into this one. And then we can also write down the V theta at this one. So the V theta at the state T plus 1 is equal to the immediate reward plus this discount factor times this one. And then we can also write down on the right side, we can also write down the advantage function here, like using different V function at different time step. So if we denote the A theta 1, if we use the state at T plus 1, and we also write down the A2 at T plus 2, like this. It's just like we spend the advantage function with like more rewards, more immediate rewards. So for the A1, we incorporate the rewards at T, and for A2, we incorporate the rewards at T plus 1, and A3, we incorporate the rewards at T plus 2, like this one. I think the advantage why we introduce more immediate rewards is because as we introduce more immediate rewards, A3 or A4 actually has less bias, but is more has much more variance. So this one has less variance, but is more biased. But as we introduce like more immediate rewards, is more variance, but has less bias.
Why do they have more variance?
Actually, I don't know. I just but the bias we can tell, because if you introduce like more rewards, you are more accurate. You are more accurate to get the advantage, right?
Okay.
I think this is because this is what we are doing is bootstrapping.
Bootstrapping?
Yeah, this is a bootstrapping strategy. Because like the V theta is a neural network, right?
Yeah.
So if we use expand let's say a 10 step versus the 1 step is the neural network starts to train. And like from the beginning it goes like the V theta is like very off.
Oh, I see.
Right?
Yeah,
Yeah.
because the rewards is predefined, so actually it's more accurate than the V value, right? And the V value is trained on data, right? So maybe the V value is not accurate, right?
Yes, that's correct. Yeah.
Okay, but you always subtracted by V theta ST, right?
Yeah, that is the bootstrapping because like we can actually like do the Monte Carlo with advantage with like non-parametric advantage function. We can do the Monte Carlo and we calculate the average. That is unbiased but huge variance. And if we use the V theta like to like learn the V theta, it is biased because it will definitely be off, but it's less variance because it is from all the output is from a neural network.
Yeah, but I still can't see why you calculate A theta 1, 2, 3, you're gonna increase the variance. Because the variance terms always have like V theta ST, right? Then the coefficient for V theta ST plus 1, V theta ST plus 2, V theta ST plus 3 is smaller and smaller.
Yes, but because like V theta is learning through the like let's say which like the policy gradient. So at first like V theta is not they cannot, so basically like they need to have a process to learn.
Yeah.
Yeah, so during the learning it will cause variance.
Oh, I see. Yeah.
And then
So I think the reason why we use like 1 step is because it's easier.
Use what?
Like only one rollout. Like we only use A theta 1. It's just because it is easier to train. And like the training process will be shorter. So the variance is like less.
yeah, but I think they are now just using A theta 1, right? You see, if you look at the GAE,
Yeah.
you're doing a weighted combination.
They use a weighted combination of the A thetas for the advantage estimation.
Yes, but I think the normal like advantage function is just A theta 1. Like when we say advantage, GAE is it's kind of like a V2 version of the advantage. So you see it's called advantage estimation. So it's always the estimation. It just depends how we do the estimation.
And what does lambda mean?
Lambda is a coefficient, like how much weight you want to put on each component.
Also, lambda is tunable. So it's not gamma.
Yeah, it's not tunable. It's like predefined. You have to.
I see.
Yeah, it's tunable. Yeah.
So lambda is different from gamma.
Yeah, gamma is the discount factor.
Okay. Yeah. Continue.
Okay, and if we define sigma t as this way, and then we can write down the advantage 1, advantage 2, 3 using the sigma. This one is just for getting the generalized advantage estimation. So if you plug into the sigma and then you get the advantage on the state and action, you can is a summation over the sigma, and this is the coefficient.
Yeah.
Okay. So finally we get the formula. So this is the generalized advantage estimation, and here's the policy, the log of the policy.
So
And
so basically, in practice, you have to decide B, right? You have to decide how many terms you're gonna sum in A theta GAE, right? General advantage estimate.
if I remember,
Yeah, here, if you look at the objective function, right? Your A theta GAE, theoretically speaking, you should sum B from 0 to infinity. But practically, you need to truncate, right? You need to truncate B to, I don't know, 4, 3, 3, 4, 5.
so because I think because the sequence has a mass length, so the B has a maximum, right?
Okay.
So yeah,
And also they also learn neural network for weight.
yeah, they use a neural network to learn the value function.
So
The
the
state
value function is learned by neural network. But the large language model itself has their own parameters, which determines P theta ANT given SNT, right?
Yeah. So I will. So we have a large language model. So actually, they use one model to train the value and the policy, but they just like use different they just change the last layer. So if you use a prediction layer for the policy, they call like LM layer. If they use they want to get the value prediction, they replace with another linear layer. It's called a value head. But they share the same body.
Yeah. So basically, they're gonna pre-train a large language model, and then they plot, they put this they hybrid this LM head with value head, and I don't know, it's
Yeah.
you just need a value head, right? Because the policy is just within the large language model itself.
Oh, they also use a reward head. So the score head for the reward model. They need to train a reward model. So, but all of the models share the same body. They just like use different. The last layer is
Okay,
different.
so they have a reward model to give you the score at each token.
Yeah, add for each immediate reward for each token.
And then they have the
Oh.
value.
So my mistake. So the reward model is not for each token. It's for the after the model give the full answer and then you give them one reward, not for every token.
But how do you get to the RT if you go back to the objective, right? You need to know what's the immediate reward after each step, right? If we go back, okay, you got RT. You got RT. Next step. Slide 10. Yeah, next slide. Yeah, you got RT, right? RT means what is the immediate reward after you perform action A on the state ST, right?
So actually, in the practice, they will calculate the total reward based on the score and the KL divergence. So then they have the reward for each step. But yeah, so I will. So for example, this is the question. So the basic means like is asking why the sky is blue, and this part is the answer, because it's the reflection of the light. And then if you so this sentence is the prompt plus the response of the model. And then if you put this test into the training model, the model you want, the policy model, like the model you want to optimize for the policy. And this is the baseline model. So once you put the test into the two models, and then they will have two sets of probabilities. And based on the probabilities for each token, you can get the KL divergence for each token. And also you need to put the prompt plus the reward response into the reward model. But the reward model only output the reward in the last token. And for all the previous token, it's just 0 reward. And then you add them like token by token, and you get the reward for each token.
So how do you compute the KL divergence? It's what does the baseline model mean?
So the baseline model, you know the reinforcement is for the fine tuning. So when do the fine tuning, you already have a pre-trained model. So they just directly use the pre-trained model as the baseline model, because when they want to calculate the KL, because they don't want to the fine-tuned model is too far away from the baseline model. Like they don't want to want the model to deviate from the baseline model too much. So
So that means like so the KL divergence is predicted between the baseline model and the what?
policy model, the model you want to fine tune.
And then the KL divergence is token by token.
Yeah, token by token. You measure the probabilities from those two models and calculate the KL.
And then how is the score? How is the score obtained?
The score is like before fine tuning, you have to train the reward model, but the reward model just give you the score at the very last token. So for example, here in the very last token, you get the reward score of 3.8. But for all the previous tokens, the reward is 0.
Oh, and then how is the final reward is obtained?
Is a coefficient plus the KL divergence, and then add the score and get the reward.
Yeah, that's okay. So they want, okay, so you multiply with a negative coefficient. So
Yeah,
basically,
negative, right? Negative.
yeah, so basically you want the KL divergence to be as small as possible because you want to maximize the reward.
Yeah.
So you want the trained model, you want to fine-tune the model to generate sequence to be as close to the baseline model as possible. And meanwhile, want the reward at the last token to align with the ground truth token.
Yeah.
Yeah, that's a little bit weird, but it's reasonable. But why do they care so much about the last token in the score?
I don't know, but actually in the DeepSeek model, they use different like reward. So we'll see.
Okay. Okay, so then my question is so go back to the previous slide. Right? No, just the architecture, the page 17. So that means like the baseline model is actually the blue part, the LLM, right?
Yeah. The parameter it doesn't get updated, so
it is frozen. But if you want to fine tune that, you need to have a policy model. The policy layer is just one layer above the baseline model.
Yeah, but in the parameter of the body, you also have to update, as well as like different heads.
Oh, so you mean fine tuning? During the fine tuning, you want to update the whole LLM?
It's like they create 2 copies of the pre-trained model.
Okay.
One copy you keep like frozen, and another copy you keep updated.
Oh, okay. So LLM head. Okay, the LLM head, as well as the LLM reference they're still used to predict tokens, and then you add one more head, value head, to for the evaluation of the value, and also have a score head to give the reward of the last token.
Oh, actually, like it's 3 copies. One copy for the frozen, and one copy for the you have to train the reward model before training the policy and the value, and then at last you train the reward and you train the value and the policy model.
Okay. But how do they train a score head?
So I will talk about here. Score head. So they use this loss. So people will like give you a question and let the models like output the answers. Like maybe they choose like they generate two different answers, and then human like label like which one they prefer, and then the chosen one, and then the model outputs the score for the chosen one and the rejected one, and then optimize the loss.
But I think it is sampled, right? It is sampled by the if you make prediction, if you use your LLM to make prediction, it is sampled sequence, right?
Yeah, you can get any number of answer samples.
And then you have labels. You have labels. Some of our labeled as chosen, some are labeled as rejected.
Yeah, and this step needs like human labelers.
And then, yeah, my question is how do they back propagate? Because
Oh, this one just the score, like for the chosen one. And this is rejected is the score for the rejected signal.
okay, so the chosen one with scores.
Yeah. It basically means it wants the chosen one scores is larger than the
Okay.
rejected ones.
But that
And
score that score is based on the softmax probabilities, right?
oh no, the score is based on the score head. It outputs a
Oh,
scalar.
I see. Okay. Oh, okay, that makes sense. So you got a score, okay.
So that means you have to input the whole answer sequence to the model, and then you get a singular score.
Oh, I see. And then the score is still based on the whole answer, right?
Yeah, the whole answer.
And then in your training, yeah, next slide. Then in your training, you just place that score at the end of the sequence.
Yeah, the very last token.
At the very last token, but that very last token, that score actually represents your overall quality
Yeah, right.
answer. Okay. Okay. Their pipeline will be given a pre-trained LLM. You first add a score layer on top of it. You use human label data to train the score model. And then you make another copy of your pre-trained LLM. You add two layers. One is actually just one more layer, right? One value layer. And then you just fine-tune the model based on the rewards computed from the baseline model and the score model, and through that framework, the average advantage gain framework.
Yeah, so this process actually requires you, like in each batch, you have to run multiple models. So actually, this is very memory costly, right?
In each batch, you have to rerun multiple. Oh
Yeah.
yeah, okay, yeah, okay. They're all based on like original huge model, right?
Yeah, original like pre-trained huge model.
Okay. Yeah. Next.
Okay, so this is the generalized advantage, like the loss. And then we also have to introduce the importance sampling. So this is the importance sampling formula. It means when you like integrate over the original like distribution, the px here is a probability. What if you have a reference like the probability q, and then you want to integrate over the q like the probability? Then you can do this trick, right? So this is the importance sampling, and then put into the reinforcement learning. Actually, they are usually like trained on the like off policy learning. It means the trajectory you sample, the policy is different from the policy you trained. So in this way, actually, it has benefits that you don't need to sample the trajectory and update the model. Like this is very data costly. So if you do the off policy learning, you can get the trajectory or the data from the reference model, and then you can train on those set of data multiple times for updating your model. So this is the advantage of the important sampling, like when you use that. So we can reformulate the here, and so p theta prime here is the reference policy. And
basically you use your pre-trained model to generate a bunch of trajectories offline, and then you use it to...
Actually, I think I mean this reference here is not the reference I talked about before. So this one, the p theta prime, actually is also updated during the training. But the updates is delayed. Like we always update the theta here, but the theta prime here we only update after a few iterations. It's not like in every iteration you update the theta prime.
Oh, okay. So, but which model contains this theta prime?
Theta prime.
Yeah, this theta prime, I mean, belongs to which model?
It is also initialized from the pre-trained model. Like from pre-trained model, we we keep another 2 copies. One is for the theta, like we train the model like every time we do the gradient descent. But for the theta prime, we only update it after some iterations, like more slower than the theta.
What's the benefit? You still need updated. You still
So
need
this is like off policy learning.
what?
It's not like on policy learning, it's like off policy learning. So it works like this. So first we sample the data from the theta prime, sample the answers from the theta prime. And then once we get that data, we can do multiple iterations of the updates to the theta itself. Like it's like we reuse the data from the theta prime.
Okay.
If we have the theta prime, then every time we sample from theta, we update the model, and then we have to sample the data from theta again. It's like we couldn't reuse the data. But if we introduce the theta prime, we can reuse the data.
Yeah, I understand. I mean, this is kind of like effectively reduce the number of number of inferences during training.
Yeah, like reduce the yeah.
Because every time you have to sample the trajectory, meaning you're going to sample the sequencer. But
Yeah.
right now you can just use the old model to... Yeah, okay. Probably you can use theta prime to generate those sequence, like 1,000 sequence, and then you just train it for many epochs, and then you call the model again to generate sequence again.
Yeah.
Okay.
Actually, like I think there's only one model. I think for the classic proximal policy optimization, there's only one model. So let me try to annotate. So you see, like we only have theta prime. Our goal is to get the theta. But like the problem is like we don't have a theta GAE. We only have a theta prime, right? So I think the whole idea of TPO is to try to control how far we move from P theta prime to get the new P theta. That's the whole idea.
So
what you are saying is the off policy is for the value-based method. The TPO is still on policy, but we are trying to mimic that situation by because we want to control how much theta prime deviates from theta. So there's only one model.
So what do you, if there is only one model, how do we like update theta and theta prime?
So theta, so let's say theta prime is the old parameters, and theta is the parameters they want to get.
I see. You mean,
Yes.
say what do you mean?
So basically, like theta. So thing is like theta prime is the old model, and theta is the parameter we want to get.
Yes, it's like I use all the parameters to generate trajectories, and then I keep
Yes.
updating.
Yeah, I see. So
parameters.
yeah, in that way we only need to keep one set of parameters. Yeah.
Yes.
Okay.
You only need to keep one set. No, I don't think so. You still need to keep two, right? It's like you use all the parameters to sample, right? Then you keep updating the model parameters to a stage, and then you set the old parameters to the new parameters, and then update, right? It's like
Yes. We need to keep the theta prime and theta really, really close.
I mean, we can actually, I think we just need to keep one set of parameters because when we generate the theta prime, get the data, and then actually we don't need the theta prime anymore, right? Because in the next sampling data from theta prime, actually we can use the new theta to get the data. So it's just a notation for the theta prime.
okay, yeah, that's correct.
Yeah. Okay, so and then we also use the formula, and we can get the final formulation. So yeah, it's the we just need to take gradient over the p theta here.
Then there's not much computational advantage of doing this, right? Because you still need to sample the trajectory.
Yes,
The difference is how do you
by doing so, like, so normally, like, if you use like policy gradient with advantage, it's, let's say, like we need like 7 million like training steps, but with PPO we only like at most like 1 million training steps. This converts really fast.
can I say it again?
So the whole idea of PPO is like we don't want to, during our update, like the, let's say Adam or anything, we want to control how much it deviates from the previous policy. Because if we deviate too much, because like as I said, like the whole problem in reinforcement learning is because variance. Because variance will more like affect on how strong we update our model. But with that PPO constraint, so with that constraint, like we don't deviate that much. So it's like variance doesn't affect our training that much. That's why like we can go to like convergence really fast.
Yeah, but I mean, from the updating mechanism to my understanding, is just like you freeze some part of computation of the gradient, right? You cannot reduce the computational graph. Like when you sample this, right? You when you calculate the gradient, actually there's no freezing as well, because what you need to is just to compute the gradient for this guy, right?
Yes.
And the only difference is that, okay, whether you want to but the calculation of this A and the P theta prime are all based on old data. Yeah, I don't know what's the advantage of like reducing the number of inferences. I don't see that. Maybe it can help accelerate the convergence, but there's no way. I mean, you still need to generate a lot of trajectories, right? You still need to generate n trajectories to update each step. There's no way you're gonna avoid generating the trajectories.
I don't think I think the problem is we only have one theta. We don't have PPO still on policy. We are not having a replay buffer.
Yeah, you only have one theta, and every time you use current theta to generate, say, n trajectories,
Mhm.
and you calculate, and maybe you just use this guy and combine this guy and this guy to compute the update for multiple steps, right? And then you
Yeah.
update the theta prime to theta, and then you keep doing this, right? What's the
So maybe there's one possibility, like, you know, the complexity of the inference and the sampling of the or training is different. If you want to sample the data, you have to sample token by token. But if you just compute the p theta itself, it's just like one time thing. So it's like you sample data like one time and then you train on that data multiple times. So that's reduce the complexity because the sampling data is costly. You have sample token by token.
okay? That means like once you sample n trajectories, you can use it for multiple updates.
Yeah. But if you sample one time and just update one time, and then actually the sampling is very costly, and then the complexity is high.
Okay. Yeah, go ahead.
Okay. So finally, we get like two versions of PPO. So PPO1 is like this one, and the add a KL between the P theta and P theta prime.
Okay.
And this is the PPO2. So in the PPO2, it just like clip the the P theta divided by the P theta prime. They constrain it has in a range. So the epsilon here is like predefined. So if this one is smaller than the one minus the epsilon or larger than one plus the epsilon, then it just clip it out. So I think this is for the stability of the training. It doesn't want the p theta too far away from the p theta prime, so it just clip it out if it's too far away.
Okay. So it's one so if it is too small, it will be flipped to 1 minus epsilon. If it's too big, it will flip to 1 plus epsilon.
Yeah.
Okay. Yeah, next, please.
Okay. So this is the loss. We already know how to train the rewards. Yeah, this is how we train the rewards, and then we can this is how we train the value function and the policy. According to this formula, and then like to train the policy and the value function, we have to get the labels for the value function, right? So there are three methods. So this one is called the Monte Carlo method, but the variance is too big because it uses all of the immediate rewards at all of the 10 steps. And this one is called the temporal difference method. And this one is called the generalized advantage method. So they are different, like how you get the labels for the value function.
So you mean during the training, you also you not only get the reward for every token, you also get the label for the value network, value layer.
Yeah, you have to get a label for the value network, and then you have to put the supervision loss for the value head.
But is it like you first update the value network and then use value network's prediction to update the policy
I
layer
think they just combine the two losses
together?
together, and yeah. For example, like if you give a prompt and a response to as a test, and then based on your reward model, you can and the KL you can get the reward for every token, right? And then this is the reward for every token, and then you want to and this one is the like state model, like the value prediction.
Mhm.
So you have to use this reward to generate your labels to supervision on the prediction of the state value. And there are 3 different methods. So I think they mostly use the last one, the generalized advantage method.
Well, how do you get ATGAE? ATGAE is also based on the current value network's output, right?
And also based on the rewards, immediate rewards for each snapshot. You can
Yeah.
see.
So you every time you update, you first call your current value network to calculate this A theta JE and then use them as the new label for the value network.
Yes. So based on this one, you can calculate the label for the current state ST, and
Okay.
then you put supervision on the
Yeah, but the label for the current ST is based on your current values network's prediction. So
Yeah.
you use your own prediction plus some correction term to update yourself again.
Yeah.
I think there's a label mistake. The one for the GAE is ATGAE plus VXT plus 1. It should not be XT, right?
Uh,
Oh, ST plus 1. Okay.
I believe so. I'm not 100% sure. I think because if you're doing this, it doesn't make sense. Like, because V label ST cannot be equal to VXT plus advantage.
so advantage is the minus this one. So yeah, if the
Oh, I see.
So
yeah,
it should subtract it by, oh no, yeah, it should be plus, yes.
yeah, plus, yeah. So that this one is yeah, it should be plus.
Okay.
Okay, so this is how to train the value and the policy. Okay, so right now is the Llama 2 paper. So Llama 2, I think it has some modification to the model structure. So it proposed a group query attention. It basically just like let's see. So if I remember correctly, you know, when you do the multi-head attention, you have like multiple QKV.
Yeah.
But what they do is just like they group all of the query heads, and then for each group they just use one value and a key value. So it just like they reduce the complexity. So they use this one. It just like the model architecture change.
So you mean they use the same query for every group?
They first they group the query embedding, right? And then for each group they use a single key and value embedding.
Oh,
It's like they reduce the number of key and values.
what's the difference between multi-head? It's like a smaller multi-head attention.
Yeah, it's smaller and like it's like yeah.
Okay.
And in this Llama, like Llama 2 paper, they try to use the reinforcement learning to make the model align with the human preference and instruction following. It's just like what we discussed. Like first they train the reward model like with human label data, and then use the reinforcement learning to train the model. And they use the PPO here. And in this one, the remote model is learnable. Like they also learn the remote model, but in the DeepSeek paper, we will see that they actually the reward they use they don't need to train it, but in the Llama paper they need to train the reward model. Okay. They also use the rejection sampling fine tuning. It just means when a model so they input a query into the model, and then the model will generate like multiple answers, and then they just choose the like preferred one, and then they added the question and answer pair to the data set, and then they just fine tune the chosen question and answers. Like they are like trying to reinforce the good one answers. They call it like rejection sampling.
So is this automatic? I mean, you mean they rank the top answers and put them in the training data again? Is it what they're doing?
Oh, let me see. So they sample K outputs from the model and select the best candidates with the reward model. Okay, so this is not like human selected, it is by the reward model. They use the selected outputs for gradient update.
For each problem, the sample obtaining. Okay, the uses the selected outputs as a gradient update. That means, okay, they're gonna rank rank the highest reward model and only update them, right?
Yeah.
Update model. Okay, this is like the risk seeking. I know if Zach is here, but it's like a risk seeking policy, right? You just pick the highest ranked trajectory and update the model, update the gradient from that trajectory.
Yeah.
Okay.
So yeah. And you know, they public the Llama, and they have to consider safety. The safety is the priority, right? So to enhance the safety, they use the supervised fine tuning and also the reinforcement learning to enhance the safety. Like for example, they will find a human to like write down like the prompts related to safety, like the answer questions, and then they use it to fine tune the model. And also they also mentioned that they also train additional reward model just for the safety, like it measures how safe is the answer and assign rewards to them, and they use it to train the reinforcement learning.
Okay, so this safety evaluation, safety score are integrated into the final reward computation as well, right?
Yeah.
Basically, you have the score model, which only is trained for the quality of the answer, and then you have some like a safety model to evaluate how safe your results are.
Yeah, so the rewards model is like two parts. One is for the like how helpful is the answer, and the other one is like how safe is the answer, and they combine the two rewards, and then
But they're also using some. They're both trained with some like a supervised learning. Some human being will provide a label.
Yeah, like you can use there are generally just two ways, like the SFT, the supervision task, and then reinforcement learning task. Okay, so this is Llama 2. And then actually there is another proposed like reinforcement learning for the large language model called the direct preference optimization. It's a 2024 paper. So they claim the objective So when if they optimize their proposed objective, actually is equivalent to the PBO update. So they prove that in this paper, but I didn't go to details, so I can just show you the loss function. So this is the final loss function.
So what's
And
the idea?
the key idea is that they, in the PBO, you have to like maintain multiple models, right? So they don't want to be so costly. So in this one, they just need to, I think, yeah, they just use the policy model. They don't need the value function, and they don't need the reward model.
Oh,
They
really?
Yeah, they maybe they can involve the reward because they just like for giving prompt, the large language model like generate two answers, and then they label them as win and loss, and then the objective just to make sure the good answer is better than the
Oh, so, okay. So they still have like this human preferences data.
human preference data, but they don't need to use the value function.
Oh, I see. Okay.
Okay.
So this reference model is can be viewed like the pre-trained model, right?
Yeah, the pre-trained model, like you don't want your fine-tune model like too far away from the pre-trained model.
Okay.
Okay, and they explain what the gradient does. Like increase the likelihood of the better answer and decrease the likelihood of the bad answer.
But they still have like a reward, right? R theta. What does R theta hat mean? Oh, R theta. Okay. So they define a reward model like this. Okay. Yeah, is this one sounds like similar to the imitation learning.
Really?
Yeah, they don't want to the imitation learning is just to give you the examples of trajectories, right? You want to encourage the model behave like the trajectories, the correct trajectories, and far away from the wrong trajectories.
Mm-hmm.
Okay. Do they claim like how it is better than PPO?
For introduction, I think
I think this is way better than PPO. The deep
Okay.
because like the problem I think with PPO is like even if they use PPO, the training is still unstable. With DPO, like what they claim is this makes training very stable.
oh they say here like up to 6 billion parameters, maybe the model is better. As least as effective as existing methods, including PPO.
Okay. Okay. Yeah, this is like reinforcement learning free. Algorithm. So when it is published?
On archive is like July. Let's search. Oh, so this one?
Yeah.
Oh, Neural Names 2023.
Okay. Yeah, hopefully it really works because yeah, because this might be very useful for our project.
Okay.
Okay.
And then reasoning. So actually, I think the most of the existing works, the reason is just based on prompt. So yeah, that's so this paper like they want to get the chain of thought by prompting only. So it's actually very simple. So if you just look at the example, so in the prompt, they just like do do a few shot learning. So in the example they gave to the model, they will include a chain of thought process. For example, like this is the question, and then when they give the answer, they will give the chain of thoughts into the answer, and they also give a like conclusion, and then this is like the few shot learning, right? And then they ask their question, and then the model will follow the example. Also, the model will give a chain of thoughts and give the final answer. So it's just purely prompt-based chain of thoughts.
So I mean the input, this pop box, they're just the input to the model.
Yeah,
Like
just the model with the example of chain of thoughts.
And then you ask another question, and the model will output similar chain of thought.
Yeah. That's basically the paper is doing.
Okay.
But yeah, it reveals that the large language model can do the chain of thoughts like without like training, right?
Okay.
Okay. And so this paper is also very simple. Like it just use the same technique as the previous one. It just like incorporate the chain of thoughts in the prompt, and then it asks the language model to output like 3 different answers, and then they do a majority vote on the answers, and they choose the most one and as their final answer. So they call it as a self-consistency.
This is ensemble.
Yeah, ensemble. Yeah.
But there's no training. It's just ask the model to give 3 answers and do some vote.
Yeah, do some vote.
Okay.
And also it's probably ICR 2023.
Yeah.
Okay, and then so this one is like they are not calling it as a chain of thought. They call trail of thoughts. It's basically it's also prompt based. So but they prompt the model like step by step. First I get a few steps, and then they will create a tree structure. Like they will use like BFS or DFS to discover the solution.
How do they create a tree structure?
I haven't go into the details, but it's just prompt based.
Okay.
So this is the process. For generating the thoughts, they have like 2 strategies. Like for each step, they have to generate K candidates, right? So they have 2 strategies. First, they can sample the candidates like independently from the COT prompt, the chain of thought prompt, and they get K different candidates. So it's K like K leaves of the tree, right? And then another strategy is that they can use sequentially like get the candidates. It just means they get the candidates in one sequence.
Is it? I mean, the procedure you mentioned here is how they provide the training data, or
Oh no, it's just like prompt based like chain of thoughts. So the idea is that not like this paper or that paper, they don't want the model to give like the whole reasonings output at one time. They just want get step by step.
Oh, so this is all about how do you let the model inference according to your need, right?
Yeah.
Okay. So then they kind of like invent the heuristics to get your best chain of thought.
Yeah, the heuristics like really depends like how you evaluate like each node in the tree, right? Like how do you want to like this node is good or bad? So
Okay.
yeah, it should be based on the heuristics.
Okay, this is like how smartly you can call the large language model to get the answer you want.
I think they also, I think they will also like reprompt the model. Like for example, they will put the model put the question and the step to the model and ask them to give a score. Like, what do you think this solution is good? Like, what do you think this solution? And the model will give you a value, and they use that value to decide like which node I should continue or not.
Okay, so if you ask a question like, how do you think this answer is good, it will just give you a numerical number?
I don't know, like is here like generate a scalar value. Maybe you can prompt the model like, hey, please give me a scalar value. Like, what do you think?
Oh, I
1,
see.
1 to 10. Like, please, like, yeah.
Okay, they also give some heuristic. You said that all those classical classification that could be heuristic turning into a value.
Yeah, maybe you prompt like, do you like what you dislike? Do you think it's true or not? Is possible or impossible?
Okay.
Like, you need to re-prompt the model,
Okay.
give you the evaluation of the current step. So yeah, this paper is still like prompting based.
Okay.
And this paper actually I didn't say so. It's a graph based. I haven't checked that. I just like know like there are people doing trees, there are people doing graphs.
They're all based on prompting strategy.
Yeah, based on prompting. Actually, those paper are actually very new, like out from like 2024.
Okay.
So yeah. And there is a zero shot like chain of thoughts prompt. So in this paper, they just discover like if you just give the model a prompt, like let's think by step, and then the model will give you a chain of thoughts. So they call like zero shot chain of thoughts.
That's it.
Yeah, that's it.
There's no other ways of to collect the chain of thought. It's just this prompt.
Yeah, just this prompt.
Let's think step by step.
Yeah, let's think by step. And they also give the model a prompt like to give you like you conclude the thinking process and give you the final answer. So this one is also prompt.
Okay. Where does this where is this paper published? Oh, it's highly cited.
Yeah, it's highly cited. Okay, so yeah, it's 2022.
Okay.
Okay. So this paper, it is discovering like, so it makes a conclusion that if the inference time is longer, if you increase the reasoning step, and then you will get a like more accurate answers. So that's it. And so
If
how
different step is more?
yeah, more inference step, then like more tokens generated, and you will have like highly accurate like answers. So they are doing this by in the prompt. They will like in the future learning, like when you give example, they will give like prompt like this one, like think about like Tokyo, think about taxi, and it's just like anyway you can increase the token, right? And then when the model like generating new answer, it will follow the step. Like maybe he will try to recheck the answer before, will rethink about one particular, think more time about one particular like the place or items. So yeah, you give some example like think about the word. You can give some prompt like think about some word, give it a more time. You can like read a question again, and also you can repeat some state. like repeat
Oh,
reading.
this is just the strategies help you to create a lengthy prompt.
Yeah, a lengthy prompt, and then is provided to the the few shot learning, right? And if you give the model another question, and then the model will follow the same prompt, right?
Okay.
And
Looks like very useful technique, yeah.
yeah, and also like self verification, like you need to give prompt like recheck your answers, and also like for math problems, they will like make equations like on purpose.
On which LLM does this paper test? Is just Llama 2 or GPT?
I don't know, let's say.
I'm just curious to know like which large language model can behave like this. I mean, if you just give a very good prompt engineering, it works. Yeah,
Oh.
GPT-4. Okay.
GPT 3.5, 4, and this one.
Okay. 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 That's incredible.
And also like compare like zero shot with zero shot chain of thought. Like they want to compare, for example, like when answering the math question, like what's the result of like without the chain of thought, and what's the result with the chain of thought, right?
It looks like their methods are pretty good. I know in the second row, like SAVMP letter coin, what's their method is denoted as auto COT or few shot COT?
I think their method is like the x-axis, like how many like extra steps for the answer, and then they evaluate their proposed like the idea on the two methods. The first method, few shot chain of thought, the second auto chain of thought.
Oh, okay.
So the two methods, like most of the results, like when they are like more inference time, like the accuracy is increasing.
I see. What's the auto COT? What's the auto COT method?
Auto COT. Okay, I haven't. This is the auto COT. So from the graph, I think so two main stages. So question clustering. So there is data set like containing the question answers. And then first for all of the questions, they use the large language model to give the chain of thoughts answers. And then they group all of the group into clusters. And then in the real evaluation stage, they will select a representative question for each cluster and generate the reasoning chain.
Okay. But then their method is just means like when they use zero shot COT with simple heuristics, but the simple heuristics will be replaced by their lengthy prompt.
Yeah.
Just a lengthy step by step. It will put much more text.
Yeah, we'll have more steps, reasoning steps.
Okay.
Okay, so I think all of the most of the reward works are based on prompting.
I see. I see.
Okay. Also, I see a few papers like they discovering like actually they can increase the reasoning ability by fine tuning. So it means that you have to create a data set, you have a question, and then you have a human written like chain of thoughts, maybe a math problem, right? And then they feed the specific data, the math data into like fine tuning, and then the model will also like have better like chain of thoughts ability. And
That
also,
fine-tuning is just based on sequence of your chain of thoughts, right?
yeah, just like fine tuning, just train the next token prediction,
Okay.
like with the specific data sets.
Okay.
And another like the I check like maybe some people will do this like they will use a very powerful model like GPT-1 or DeepSeek, and then they input the question, and then they let the models like generate the chain of thoughts, and then they collect the data, and maybe they filter some out and get some high quality chain of thoughts, and then they use those to train their model, right?
I see.
Okay, so also people started to use reinforcement learning to get the chain of thoughts. So there are two different directions. The first is the outcome reward model. So it just means the word is given when the whole answer is generated, just like how we discussed in the PBO stage, like the final reward is given just to the last token, only when the answer is obtained. And the other direction is the process reward model. So the idea is that maybe there is a case like the immediate steps, the recent step is correct, but the final answer is wrong, or the steps are wrong, but the final question is right. So the previous like outcome reward model is not good. So they propose to evaluate each step by step. They will give you reward for each reasoning step, right?
Oh, one question. So you said outcome reward. This method it follows the same PPO pipeline, right? It's just your training now becomes becomes based on the chain of thought.
So I think the idea just like how like use like two different rewards. So for this one, it's just like just like PPO like discussion, like we use like one reward for the whole answer.
And that reward, okay, that reward is still based on you have some score model, right? Are trained to evaluate your chain of thought quality.
Yeah,
and then the last token, and also you want to calculate the KL divergence, you add them together, you got some like a final reward for every token you generated, and then you threw them into the PPO pipeline.
Yeah. It doesn't care about like if your immediate like your middle steps are correct. You just like
I just want to confirm that this outcome reward model, the methodology part is exactly the same as PPO. The only difference is that your training of the reward model is based on the chain of thought data.
yeah. So yeah, let's check this paper. So they have like two stages. So the first is one up, and the second is reinforcement learning. So in the one up stage, they will collect data set like include the question and chain of thoughts, and then they just fine tune on this data set, right? And of course the reward is just based on the oh this stage just one up, like just fine tune the question and chain of thoughts, and in the reinforcement learning. So
Online self-learning using dataset comprising question answer tuples. Yeah, they still use PPO, right?
yeah, PPO. And here, like the reward is 0 if the answer is like non-terminal state. It means like maybe it doesn't give you an answer, and then the reward is 0. And If it's 1, is correct. If 0 is wrong. So, it's just the outcome-based reward.
But this reward is given by human beings, right? You need to know if
Yeah.
the answer is correct or not, right?
Not necessarily. Like, for example, you have a math data set and data set have question and answer. Maybe the answer is just a scalar. And you can let your model like after train of thoughts and output a scalar, and then you just need to compare the scalar with the ground truth. So it's a automatic step. It's not don't need to be checked by humans, right?
Oh, I see. Okay. And then they follow the PPO pipeline.
Yeah, just follow the people. So everything is the same. And another type is the process remodel. So it has to make sure the middle step is correct. So yeah, so there's a process review model. And then the first thing they need to do, they want to do is that they want to design a reward function, right? So this is how design reward function. So they have a problem, and then they will prompt the model to generate the next step, just one step. And then they calculate the reward for this step based on the potential. So the potential, they define the potential as, say, okay. So the reason step as its potential to deduce the correct answer. It means, for example, if they see the step, and then following this step, you can finally get the answer right. Maybe so they need to sample a lot of times. Like they calculate the number of correct answers from all of the trajectory, like is a percentage, and then they that is the potential for this step.
Oh, okay. So it's like at every step you just given that step, you let the model to
Continue inference.
continue inference and see the final answers.
Yeah. You have like sampled this like multiple times. You have get like a lot of answers, but you need to calculate the percentage of the correct answers. Okay.
Yeah.
So based on this, they can train the process reward model, and
Okay.
then they can use this reward model to do the reinforcement learning.
So they don't need to train a score model, overall score model. Or they have some like a process annotation, they use that to train a score model, a reward model.
I'm not sure, but I think maybe they still need to train a remote model, but they have the labels, right? They have the labels.
Yeah, they have their reward model can predict the reward at every step.
Yeah.
Okay.
Okay, so there are two kinds of directions. And then we can finally get to the DeepSeek.
Okay.
So the DeepSeek, the biggest difference like from the DeepSeek from other papers is that they actually they don't want to train a reward model because they claim that in reinforcement learning the model is very easy to cheat on a reward model. It means even though your answer is very bad, like maybe it's not human readable, but the reward will be very high, and then that will be very bad, right? So they don't want to train a reward model. Instead, they just like design a reward function. So they have like two criteria. So first they evaluate the accuracy. But this one I think is just based on it has to depend on different like problems. Maybe based on math, it's the final answer, and maybe it's like multi-choice question. So they have to like write a lot of codes for the accuracy wasn't right. And then they also have the format rewards. It means they need to like they need to the model to put the thinking process between like two tokens. And also they need to have the model to output a final answer based on the thoughts. So it's just like they need to the model like follow this format. So they create two kinds of rewards, but it's not a neural net based, it's just like the rule based. Okay. So this is the reward modeling. And then
So they don't follow, if the answers don't follow their format, the reward will be small, and the accuracy is not correct, the reward will be small, right?
yeah.
Just okay. Just a set of heuristics to give the reward number according to these two aspects.
Yeah.
Okay.
Actually, they will also incorporate another reward. So I think is consistency. Yeah, they actually use another reward, but in the like other steps. So this one, they just discovered that when the model generate answers, they will have like mixed language, but this is not people wanted. So they design another reward, like it measures like how the answer is consistent in one language, right? So this is the third reward. Okay. So before the DeepSeek, actually the latest model for before the DeepSeek V3. So DeepSeek V3 is a pre-trained model. So everything they do in this paper is based on the DeepSeek V3. Let's check the training process. Okay, so the first thing they do is they first like develop the DeepSeek R1 0. So this model is purely applies the reinforcement learning directly to the base model. It means that they don't do any like supervision training. They just like apply the reinforcement learning to the DeepSeek V3. And then in this like experiments, they discovered that you can see this is the accuracy of the DeepSeek R1 0. So it's just purely reinforcement learning. So it doesn't have like supervision. And then you can already see the performance as more training steps to accuracy. I think this is a math data set.
Okay, so a purely reinforcement learning, what does it mean? It means like PPO?
Oh yeah. So they train the reinforcement learning like based on the GRPO. So in
And it's a variant of PPO.
Yeah, it's a variant PPO. So, but this one it doesn't have a value function. So, when we do the training loss, we have to calculate the advantage over the. It's based on the value function, right? But in this paper, they don't need to calculate they don't need to learn a value model. So the advantage, they are actually, for example, for question Q, they sample group of outputs, right? And then to calculate one output over the average output, they just need to, do the average and do the minus. Like here, the RI minus the mean and divide by standard deviation, and they get the advantage. So that's it.
Okay, that's their first version.
Yeah, this is the V0, the first version. And in the training, actually, there is a very interesting phenomenon. Like, so there is no supervision. So somehow the model, like they say the output of model, actually the model learns how to how to put more thoughts onto the process. Like it's learned by reinforcement learning. there is no like supervision, like there is no like the instruction like tell the model like you need to think about more time. There's no such thing. It's just like purely by like it's an emergency. It's a emerge, yeah.
So okay, but when they train RL model, even they don't need a value network, but they still need a score model, right? They need the score model give the reward.
Yeah, it's more just like rule-based rewards, just like here. They don't need to train the reward model. It's just like rule-based.
Oh, so okay, so their DeepSeek R10, their reward model is just based on their heuristics. They
Yeah,
do not,
heuristics.
okay. And what's the next? And also, what does the blue curve mean? In the figure, it showed a comparison. Yeah, what does the blue curve and the red curve mean?
So these two curves are all like their model, and those two lines are the O1. So this is the performance of the O1, and it means that over the 18,000 apples, like their model is comparable to the O1 steps.
A red line, the blue line shows like R1 0 pass at 1. What does 1 and 16 mean?
I don't know. So maybe it's just the some matrix in the for the math problems.
Okay. Okay.
16, I think maybe it's like they generating like 16 answers, and maybe they do a majority vote or something. But this one just
Oh, I see.
one answer.
Yeah, that's okay. That might explain. That might explain. Yeah. Okay.
Yeah, the 16 answers, they usually higher than the like if you just generating one answer, right?
Yes. Okay. And so this is just the 0, right? And what's their next version?
So yeah, so next, let's see. So they 2.3. Okay, so next version they are trying to train the DeepSeek R1. But in this time they don't like purely doing the reinforcement learning. So they still like first they do a supervision training because because they claim that if just the one R10, actually even though you prompt the model and they give you 10 thoughts, but there are many like many things you don't want to say. Like for example, it will give you like mixed language, right? And also they will give you some output some sentence that human barely understand. It's not understandable. So they claim that they still need to use the supervised fine tuning as the code start.
The
So
supervised fine tuning is still based on some like chain of thought data.
yeah. So here he introduced like they collect a small amount of long code chain of thought data to fine tune, right?
Okay.
To collect such data, they explore like several approaches.
Okay, those data sets are collected by themselves. It's not public data.
Yeah, they can prompting the model to generate chain of thoughts, right?
Yeah.
They even like prompting the R10 to output the chain of thoughts.
And refining results. Okay.
Yeah, and they want to human and animators to like check the answers and filter those like low qualities, right?
Okay.
So first step, they just like supervision fine tuning the V3 the V3 based model. And here they explain why they need to like fine tune first, like readability. And also they want to design the pattern for code start data with human priors. Like they want the answer like align with human preference, right? So they need to first fine tune.
Okay.
And then they apply the same reinforced learning process to the fine tune the V3 base.
Okay, what's V2? Where is V2?
V2, V3.
V2. I mean, you got R1, right? R1, and then you do supervised fine tuning. That's R2, right? I was confused by their versions.
They just called the DeepSeek V3 base after fine tune. They just I think they don't give you a name.
So okay, so they have their DeepSeek R1 0, or they have their base model, and then they do some fine tuning. They got the DeepSeek V3 base.
Oh no, DeepSeek V3 base is a base model for the DeepSeek R1 0, and also they fine tune the DeepSeek V3 base.
Okay, yeah, that's my understanding. And then they after the fine tuning, they do the reinforcement learning again.
Yeah, they do the reinforcement learning based on the fine tuned V3
Okay.
base.
Okay.
And then in this step, actually, you can say they check that the prompts, the language are mixing. So they introduce a language consistent reward during this reinforcement training.
Oh, I see. So they actually adjust the reward.
Yeah.
Those reward is also computed based on heuristics, right?
Yeah. Heuristics. Okay, so next they do a like reject sampling and another like supervision fine tuning. So it means so when the like reinforcement learning model converges, they just like load the checkpoint and collect the supervised fine tuning data. It means like they give you the model answer and let the model to generate the chain of thoughts, and they collect the data like this, right?
Yeah, once the generate, what's the next step?
So I think the next step, so in this step, they generate two types of data. So one is reasoning data, and the other one is non-reasoning data. So the reasoning data, yeah, the non-reasoning data, like for example, like maybe the writing or role playing or something. Anyway, they have two types of data, and they has like and then they fine tune the DeepSeek V3 base for two epochs with the collected data. So it's not fine tune the pre-trained V3 base. They get another V3 base and fine tune on that data.
Oh, one second. So how are these data sets collected? So they're collected by prompting the current version, DeepSeek V3, right?
Yeah, they prompting the fine-tuned and the reinforced learning
Yeah.
with three base, and then get the reasoning data and the non-reasoning data.
But they need some like annotators to make sure this is correct, right?
Yeah, so that's they call the reject sampling. Like they sample a lot of answers and then they just like collect the best one. And also they noted that they also feed in the ground truth and the model prediction into the DeepSeek 3 for judgment.
Okay.
Maybe it's a mix of like human and
Yeah,
the
yeah.
Seek V3.
Yeah.
Okay. Anyways, they fine tune get another DeepSeek V3 and fine tune based on that kind of data. It's not based on the previous model.
Okay.
And then the last step, like they do another reinforcement learning for all scenarios based on the fine-tuned DeepSeek V3 base. So
The Deep V3 base is still okay. I'm a little bit confused about their training process. They got this data to fine tune DeepSeek V3, right? And then they apply the reinforcement learning again.
the first time for the DeepSeek R1, the first reinforcement learning, after the first reinforcement learning just for collecting the data. The second reinforcement learning is not based on the first reinforcement learning model.
Yeah.
They get another V3 base, and
Yeah.
fine-tune and do the reinforcement learning.
And finally, they got an even better start model, right? And then they do reinforcement learning again.
Better star model, you mean?
Yeah, so my
Oh, yeah.
that you got the base model, right? This is your base model. You first run the reinforcement learning to get I don't know, it's called 0, right?
R1 0.
R1 0. This R1 0 will help you generate data. Will help you generate some data, right? And then use that to fine-tune this base model again to get V3, right?
To fine-tune this one, to fine-tune and apply reinforcement learning to get another set of data.
Oh yeah, fine-tune and apply. Yeah, fine-tune, apply to get, and then get another set of data. Now you use this data to fine-tune this guy again, fine-tune the baseline model again.
Yeah, fine-tune this one again, and then do another reinforcement learning.
And then doing another round of reinforcement learning.
Yeah.
Okay.
So yeah, that's the whole process. And they also do a distillation like over the other open source models, but this one they just use the 800,000 samples, like from this step. They use these samples just to fine tune the open source models. And for the open source model, they don't do the reinforcement learning, and already prove is powerful.
Also, they use the generate the data they collected from their iterative training cycles. They use that to distill from other models.
Yeah. And they don't apply reinforcement learning, and then actually the distilled model already have the ability of chain of thoughts just by fine tuning.
Then this chain of thought comes from what? Comes from those open source large language model itself, or comes from the fine-tuned data set?
Comes from the fine-tuned data set.
Okay.
Because I think this base model actually they just like pre-trained model.
Mm-hmm.
They are not even like fine-tuned by instruction prompts, right?
Yeah.
They just like, oh, maybe not because it has like this math. Maybe it's fine-tuned, but actually, it shouldn't be like have the ability of chain of thoughts.
Okay, so can we go back to review the whole procedure? So you first apply reinforcement learning with some heuristics-based rewards to get DeepSeek R1 0, right?
Yeah.
And then you use R1 0 to generate some kind of data. What kind of data it generates? I kind of forget.
Just like chain of thoughts data, but they is a post-processing by human.
Okay, it generates a chain of thoughts data. And how many examples did they collect? They did not see that.
Yeah, we don't see that.
Okay, and then they use this data set, chain of thought data, to fine tune the base model again, and then run the reinforcement learning again. They get V3, right?
Yeah.
And then they use that model to V3, and then they use that model to get reasoning data and non-reasoning data.
Yeah.
And by this time, this reasoning data, non-reasoning data, isn't like reasoning data? It's also like chain of thought data.
I think it should be, yeah.
Okay, it has reasoning data and unreasoning data, and then when they collected and annotated and filtered by human beings, and then use that to fine tune the base model again.
Yeah.
And now, yeah, then the question is, do they merge this data, like this reasoning and unreasoning data, with the previous round of intermediate data together to fine tune the base model? Because your second round of RL training, you have collected some data, right? Some chain of thought data, right?
Yeah,
And after that, you have collected another like piece of another set of reasoning and unreasoning data, right?
so I think it should include the data before. They said they expand the data.
Data set, okay. They expand data set and then fine tune that again, fine tune the base model again, and then they do reinforcement learning based on all the data they have in hand, right?
So yeah, in total, like they have 8,000 case samples. It's like
Yeah, 8,000 K is pretty it's not small. And okay. And their reinforcement data, where is their reinforcement data from? Is some open source data, or they prepare the reinforcement learning data by themselves?
you mean questions?
Yeah, they say in reinforcement learning, right? You can use reinforcement learning, but you need to prepare some data, right? Where are the data from? Like,
But for reinforcement, you just need to prepare the questions, right? So
you
I
don't
don't
need to prepare the answers.
know.
You need to calculate the accuracy, right? You need to calculate accuracy and format, right?
The accuracy. I don't know. They
Yeah, can you go back to the R10? I just want to look at what kind of data set do they use for reinforcement learning. Oh, they didn't mention that. Yeah. Yeah.
yeah, they didn't mention.
Okay. So the argument of DeepSeek is how do they get their base model? They never talk about where the base model is from.
You mean base model like V3?
Yeah, V3 base. I mean the base from some base model, they either do reinforcement learning or they do fine tuning and then do reinforcement learning, right? They just run several cycles.
It's like they collect like more accurate chain of
Yeah,
thought.
I mean, from their paper, looks like they have some base model, right? They have some base model, and then they do, they do 3 rounds of reinforcement learning, right?
Mhm.
And the first round reinforcement learning based on the history words is to generate some like chain of thought data, and you fine tune this base model, and then do reinforcement learning again, and then you use this new model to generate additional data, and then fine tune the base model, and then run reinforcement learning again, right?
Yeah.
But they didn't expose like where is their base model, right? What is their base model, right?
Base model, I think it has a paper. So
Okay.
yeah, there's I didn't read the paper, but yeah, there's the architecture. So they use a mixture of experts,
Okay.
and they invented the multi-head latent attention to
Okay.
like reduce the computation.
Also, they train a base model from scratch from their
Yeah,
use
yeah.
their own
Scratch.
architecture.
And they also use the RMS and NOR. RMS.
Yeah, then the question is why I saw the Medium says DeepSeek is distilling OpenAI.
because maybe they can collect the data by prompting the ChatGPT O1, right, to get the chain of thoughts.
So I mean okay.
But
So they're collecting data.
yeah, how they collect the data?
Architecture themselves.
Yeah. In the paper, they just say they collect the data just by their model, right?
Okay. By the base model, how are they trained? How did they collected the never
Also,
yeah.
for training the R10, they didn't mention like how they get the data for training the reinforcement learning, right? They could be like they collect this from the O1, right? But they didn't mention about that.
Okay, so it's unclear if their reinforcement learning training data is from OpenAI or their base model training data is from.
Yeah, we only know that in the second 3 iterative steps, they generate the data from their model.
Yeah, this is like a boosting, right? It's like a self-boosting. Okay.
Okay, so this is the DeepSeek, and then like this is the paper from Stanford, the S1.
Okay.
So this paper so they are claim the same idea, like they want to scale the testing time or the inference time to get like more accurate answers. So they have just like it's also like prompting based method. So they invented like two kinds of steps. So I think one step they call like budget forcing. Like they want to you can imagine like you want to you want to make sure the answers have the minimum number of tokens and a maximum number of tokens. So they did this by if the answer like it doesn't have it doesn't meet the minimum number of tokens, and then they use the weight prompt to let the model like continue the reasoning. They just added a weight prompt into here. And then if the answer like exceeds the maximum number of tokens, and then they just put a final answer prompt to early exit the reasoning step and just directly output the answer. So that's their choice. And then for the weight prompt, they can add the weight like multiple times to increase the reasoning steps. And then they test this on multiple models, and then they see the results. So this one is like how many times of weight they append to the prompt, and then this is accuracy. And this graph they compare with the majority voting. It's like they prompt the base model like generate multiple answers, and then they do the majority voting and get the answer, and then they compare their proposed model with the smart method.
But this how do they provide? So there's no training data, right? This is just
yeah, it has like in addition to the prompting, they also like they train their model. So they grab the open source model. It's what's the size? Oh, they grab this model. It's a 32 billion instruction model, and they fine tune this model with a high quality chain of thoughts
okay.
like pairs. And they also like introduce the data, how they get the data. So I think they use a Google or something. Yeah. They call the data sets as the S1K, and then it's like 1,000 questions paired with reasoning traces, and answers. So they distill this from the this is the Google's large language model, right?
Mhm.
They get data from here. Actually, I think they collect a lot of samples, but they filter that and just keep the high quality 1000.
Mhm.
And then they use this data to fine tune the open source model.
So this open source one after fine tuned and then combined with their prompting technique to achieve the reasoning ability.
Yeah. They combine with their prompting.
Okay. And then that means that their prompting will be some kind of like a dynamic process, right? You probably just want to see some results and you say wait and prompts the model to generate more, and if it is over the budget, you say the final answer is, and then the model will give you a final answer.
Yeah. They forcing like this is 2048 maximum thinking tokens. This is like more tokens.
Okay.
So actually, like they compare like two kinds of scaling of inference, like sequential and there are like two kinds of scaling methods, either sequential. In their method, they are doing sequential, right? If they add the weight prompt, then the model continues to generate data. And there is another way, like parallel. And this one is inside their baseline. Like the model parallelly like generate multiple answers and then do a majority voting. And they prove that the sequential, like with their method, is better than the like generative answers.
Yeah, if you do parallel, you cannot do sequential, right? It's just to do parallel and they generate n answers and then do the vote, right? If they do sequential, you just step by step.
Yeah, step by step. Like there are two kinds of like increasing the test time.
Okay. Okay. That's all I want to introduce.
Yeah. So yeah, that's it. So that's all of the paper.
Okay, very good. Very good. Yeah. Yeah, looks like so I saw that for the DeepSeek there's some like a distilled version of DeepSeek, or they release their own version of smaller version of DeepSeek, or they just give you the data set and you can use that to fine tune or distill open source models.
So yeah, I think they released the like the data.
Okay. So they use data set and and people use this data set to distill those open source models.
Those open source models are distilled by themselves, and they should have like released the parameters for those models.
Okay, but they never they don't release the distillation of their own model.
I think so. So maybe, yeah.
Okay, interesting. Yeah. Yeah, looks like those are all just like a engineering method, right? There's no novelty. I mean, in terms of methodology, but it's just engineering tricks.
I don't know. I don't know what's the key point of the like. What's the how do they like succeed? Like, is the reward model design, or is the like refinement steps? Like, I'm not sure. What's the key point?
Yeah, I don't know either. But this is just they just tell you if you want to improve your reasoning capability, this is a way of doing this, right? But perhaps I think probably the most important thing is the heuristics based reward. If you want to do that, that means like you have to use more more data, right? Because if you want to train a reward model, I don't know. I mean, if you want to use heuristics, and heuristics applies the range of heuristic applied will be much more narrow than learned surrogate. And that means like you probably need to you need to collect the more reinforcement learning data.
Yeah, and also like for some like some tasks I don't know how to like formulate the accuracy reward. Maybe some answers they are not either wrong or right. They're
Yeah,
like based.
yeah.
How do
There-
you evaluate that
heuristics.
kind of question?
Yeah, there are detailed heuristics about how to give the accuracy reward. It's not clear.
Yeah, this one is not clear.
Yeah.
And maybe this is a key point. Like, how do they succeed?
I don't know if they release their code, right? But the code they're just doing this is just the inference code, right?
Yeah, they just inference code. There is no like training.
Oh, so okay, so we actually don't know how you cannot say how they define the accuracy reward. How the
Yeah.
input accuracy reward. Okay. Yeah, I think that's at least we have several ways of doing what we want to plan, right? What do we plan, right? Like the simplest way might be like just the prompt engineering, but that might not be reliable enough. Another is like a fine tuning, right? Fine tuning plus the reinforcement learning. Actually, I very much like the DPO paper you quickly mentioned, because that one you don't need to train a value network, right? It looks like it might apply to the data set we have now. And maybe we can, I mean, we can do this, but we need to find a very small distilled model. Right, so we can use whatever, like the distilled model by DeepSeek or any other open source, smaller open source model, and doing this.
And for the reasoning, like our data, we don't have like step-by-step reasoning steps, right? But maybe we can use like other like O1 or DeepSeek to generate the reasoning steps and do the fine tune.
Yeah, but maybe I mean later I will show you the data. That dialogue. I don't know if in Lee here. The dialogue data actually is similar to like chain of thought.
Really?
Yeah. It's
I
like
have the data now.
what?
Oh, I'm here. I have the data, I think.
Oh, okay. Yeah, Lee, maybe you can share the data to Dan and let him take a look. Dan can click the sharing. Yeah.
Okay.
Yeah, for other people, yeah, you guys can just leave. I mean, it's very late. I'm sorry for this lengthy seminar, but I believe it's very, very useful.
Sorry, give me a second to find it out.
And also we can choose like do the outcome reward or the like process reward. But I think the outcome reward will be better, right? So and it's like if we choose the rule-based reward or neural nets-based reward, if it's a rule-based reward, then if we have the ground truth, maybe maybe it's some like disease or something, then we don't like so much human label, right?
Yeah. The reward function itself does have some like you can see that this is like a lineage. This is like one line represents one.
Yes, I use this to train the GPT-3. Yeah, to do the fine tuning of the GPT-3.
Mhm.
And I think yeah, but I just do the experiment. And now all of our data is like this. It's like we have this is the user. And we have user and the assistant. And then the user will explain what they're feeling. And then the assistant will go ahead to ask some questions.
So, does the data contain some chain of thoughts? Is there an example?
It's more
No,
like
it's generated from the audio.
there's no tag here. It's just the sequence of a conversation. You see,
Yes.
yeah, I'm doing pretty well, but I'm kind of concerned about something. And then you see the doctor says, yeah, sometimes I have problem with my attention, blah, blah, blah. And then the doctor and the patient are interacting until the doctor gives some conclusion.
I mean, the reasoning, like if I go to hospital, like I'm telling my like how I feel, but usually the doctor, they don't analyze my situation like in front of me. Maybe they just think about in their head and they just give you the conclusion. If we in this way, then maybe we don't have the chain of thoughts, right?
Oh, okay.
Oh,
So that in that granularity, no, there's just like a recorded conversation between the patient and the doctor.
right.
Yeah, there's no like the thinking procedure inside the doctor's brain.
Yeah, so usually like in math or something, like we have to decompose the
Yeah, math is like that, right? So but I think in diagnosis, you don't need that level, right? If it's that level, that's too many, right? That's too much. You can view this is a rough reasoning chain, right? So the doctor answer the question, the doctor asks the questions and then get the answer, and then the doctor asks another question, get the answer, and eventually leads to the conclusion, or
Yeah.
leads to the the cure, right? The method to cure your disease.
Okay, so if we compare with like the math chain of thoughts, like usually like they propose a question and the bot or the large language model like thinking about how to solve the problems like step by step, and then they give the answer. But here, the step is like this, like the doctor like propose like a question, and then the patient like give the answer, and then again the doctor ask a question, and then the patient answer the question. This like is like different from the math chain of thoughts, because the math they just ask the question one time, and then the language model just think like
Yeah,
in
of course.
steps.
Yes.
Yeah, it's different. Yeah, it's obviously it's different. There's a this is not exactly the same. But we can try.
So what if like whenever a patient like answer the doctor's question, we put that answer as the thinking process of the large language model? I don't know.
Yeah, that's my
Like it's like when the large language model is thinking, they ask then they ask themselves, but the answer is actually is from the patient.
yes. Yes. It's like you put this whole session of the conversation as one chain of thought. That means like if you want to do it, you want to finish your chain of thought, you need to interact with users. It's not like once you get a question, you just thinking until you get a result, right? You need to dynamically interact with users. And sometimes you need some like personal data, right? You need to have some like conditional information to fulfill the next step.
Mhm.
And also we have the history information because every time when they go to have the health decision, maybe to interact with the AI chatbot, we have their baseline survey to have their history information about their physical activity, sleeping, and those kind of data. I'm not sure if those type of history information can be used to train the chatbot.
Yeah, this might be. I don't know. I mean, just I just want to I mean, right now I just want you to show this data to Dan to give him some kind of sense. There's some like difference from what you have seen from the paper, right? From the solving mathematical problems.
Okay.
Yeah. But that might motivate some like interesting development. It's not just copy and paste other algorithm.
Mm-hmm.
Okay. So Lee, you said you have used that to test with GPT-3?
3.5, I think it's
Okay.
yeah. But since I only use only those small part of data, so it and then I embed the fine-tuned model to Facebook Messenger, but it performs bad. I'm not sure if it's because of the data or yeah. Only
What are
use
you
small.
testing? Like how are you training?
Yeah, I use a base model of GPT 3.5, I think, and then do fine tuning, and then it
So
trained it.
I mean, how do you test? Like,
I asked after I trained it, and I asked some questions, and then it replies very, how do I say? It's not what I want the answer.
so when you test, like you pretend you are a patient, like you tell
Yeah.
the situation, and then the model like give you suggestion or something, and then
Yeah, and it cannot give me a very good suggestion, and also it cannot understand me very well.
okay, I see.
So, but I think we have more data now, and maybe, yeah, I don't know.
You fine-tune on GPT 3.5. Do you have the source to which machine are you used to fine-tune?
I use API. I can show you the code, I think. Yes, this one.
Oh, GPT 3.5.
Yeah, I use their API, and since it costs some money, so I just do some experiment. If I use a lot of data to train it, I need to spend more on that.
I mean, based on which machine do you train that?
Oh, which machine? What's that mean?
So you train on some cloud? Because it's a model, right?
So
I didn't use any cloud.
so you are training like maybe using like in OpenAI as a server.
Oh, yeah.
Okay. So it is like
Use OpenAI's platform.
is free or is
It's not free.
not free? Okay.
Also, okay, so Yang gives you some money to.
No, I use my own money.
Oh, really?
Yeah, I just want to do an experiment.
Okay.
Okay.
If it can
Yeah,
work.
you don't need to do that. That's too many. Yeah, I mean,
No.
yeah.
It
Yeah,
not cost much if I just use a small number of data. Okay, yeah. That's
okay, great. So yeah, thanks, Lin. I think we should meet sometime like next week,
okay.
and we should discuss what's our first step. I don't think you need to call OpenAI API anymore. our goal, at least the goal from Yang and I are now trying to get this done by a super big model, because if you have a super big model, you even cannot make it runnable by ourselves, because the model is super huge, right? You have a big infrastructure to support the application of that model. So our plan will be, okay, we're gonna train some like very small model, maybe just can be loaded into one single GPU card. And by the way, we're gonna have some like a fine tuning and also reinforcement learning technique to work specifically for your task. That's our goal. Of course, there might be another way. You just do prompt engineering, but that means if you do prompt engineering, then you have to rely, you have to purchase some OpenAI account, right? You just throw the prompt to OpenAI and collect the results. There are two ways of doing that, but I think from the research perspective, we might prefer developing our own model, our distilled small model.
Also, if you use API, you cannot change the model architecture or the training steps, right?
You can only rely on the model itself, right? If that model has already very powerful, and then you just define a smart series of prompt, you can get the answer you want. You cannot, if that model is weak at this for this specific task, you cannot improve it.
Yeah.
Okay, yeah, that's good. Very good. So yeah, I think I'll try to schedule a meeting next week, and then we should start some like initial idea and start trying. Okay. Okay, great. Yeah.
Thank you.
Yeah. See you.
Bye.